ChatGPT.
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 ChatGPT is on everyone's lips right now, and we wanted to learn how these large language models work under the hood. Therefore, we implemented our own language model based on the Transformer architecture, the same architecture behind models like GPT-4 and Llama. Here we see an overview of the architecture that we've developed. Even though we use the same architecture, there are two main differences between our model and the popular ChatGPT.
ChatGPT.
Firstly, our model is a document completer. It is not an assistant. It just completes sequences of text. This is because we have not done fine-tuning or reinforcement learning after the initial training stage. Our model is what is commonly called a base model. And secondly, our model is of course way smaller. GPT-3, which the free version of ChatGPT is built on, has around 175 billion parameters. Our biggest model has just shy of 10 million parameters. But it is still a pretty large model compared with the vanilla RNN developed in assignment 4 of this course, which had around 32,000 parameters. We want to give you a quick taste of how the transformer learns before going into our results. In this part of the architecture, the attention mechanism occurs. The attention mechanism is a communication mechanism between the input tokens. Each token asks for information from other tokens and decides on how much attention to pay to each of them. This mechanism allows the transformer to get a good understanding of how the tokens relate to each other. As in this example, we have the sentence, "The animal didn't cross the street because blank." When generating the next token, the token it, that token attends most strongly to the animal, since that is what it should refer to.
So now that you've gotten a feel for the architecture, let's move on to our experiments. In terms of data, we used a concoction of Wikipedia articles and mostly fictional books. Our hopes were that using different genres of text would give us a more well-rounded model. Our training set ended up consisting of about 20 million characters. For the first part of our project, we did some hyperparameter searches to gain insight on what values to use. And then we set out to do some bigger experiments. One of them was to test the effect of the data augmentation technique back translation. So what that means is that we generated more data by translating our training data from English to French and then back again. And just like that, we could extend our data set with a bunch of new data, which had the same sound meaning as our original data, but expressed differently. And to test if this was effective or not, we first trained a model on the original dataset and got a test accuracy of 64.3%. And then we trained another model on the dataset with data augmentation and got 64.8%. So this was obviously not the overwhelming improvement we were hoping for, and it indicates that the dataset we had to begin with was already large enough in relation to the model, so adding more data didn't really help.
What we have done so far has been on a character level. What this means is that when generating text, we generate one character at a time. In our next experiment, instead of generating single characters, we generated chunks of characters. To do this, we used byte pair encodings. Byte pair encoding finds common pairs of bytes and represents these as single tokens. These can be entire words, parts of words, or single characters. Now, let's look at some of the outputs generated by our character level model and our byte pair encoding model. As you can see, the byte pair encoding model generates more reasonable text. This was expected since the models have the same context length, which meant that the byte pair encoding model saw more text during training and was able to learn how to create actual sentences. At the same time, the character level model had to struggle with learning how to spell the individual words.
And that was all for us, guys!
ChatGPT.